All right, let's start. Okay, we are talking about binary tree. This is something new to you guys. Okay, so right now, what the kind of data structures we are dealing with, they are all they are all very linear in the sense that usually we just add one to the back, keep on adding to the back, can add to the front. It's just one line of basically one. There's only a single path that you can go down. That's how I look at it. So if you look at your list and your tuples and your dictionary and all right, you can basically iterate through them and then get to the other end of it. So this one is a bit different. Let me just go away to the top here. So so in this case, a tree here is a non-linear data structure. Okay, so the keyword here is that is hi, hi, hierarchical. Okay, so that means there is that this tree we think about it, right? It's not is an upside down tree. Okay, because we call this guy the root, and then each then you can just imagine that these are branches that will branch out. Okay, so there are some terms that need to be very familiar with. So basically your data, okay, each item, right, is stored in a node. Okay, so all is represented by this round this dots, this round circles here lah. Okay, and nodes are connected by edges. All right, so if you look at this set of this diagram here, right? If you see where my mouse is over right now, right at the bottom edge, right? This maintains the connection to the previous node above. Okay, and if you lose the edge, if you lose this connection, right, this piece of data is no longer inside your binary tree, as in you cannot access it directly already. Okay, so there is of course the root and goes all the way down. Later you'll see that these are called leaves as well. These are called leaves. Right? So then there are some as the name goes, right, is binary. So you can okay, every node has one parent except for the root. So what this means is that at every node there is one more node above it. Okay, that is linked to it, except for the root. Because root is the start, so there's no the root doesn't have a parent. Okay, then every node can have 0, 1, or 2, 1 or at most two children. So if you look at some of the nodes here, right? Let's say this one here, this has no children. Okay, and then this one here has two children. Okay, and let's look for one that has okay, we don't have one with one children here. Okay. So just get the terms right. Okay, so the first node here is always known as a root, and then subsequent nodes, okay, if they have child, right, if they're children, right, then they can be called a parent root as a parent node as well. So this parent node, and then these are the two child nodes. Okay, so they're linked up this way. All right. So basically, you can think of this like your family tree lah. Your grandparents have you, and then no, your grandparents have a parents, and then so on and so forth. Okay. So then there's a child. Okay, so the for each child, right, there's also a left and right child as well. Okay, so each parent can have a left child, can have a right child. Okay, here we are still not concerned about how we put in the data. Is there any structure we follow? So basically, if we later you'll see that there's a binary search tree, right? That's slightly different. So we just now talk about general tree structure first. Okay. There are things like this. Okay. So if you have the same parent, you're called siblings. Okay. I think this is quite straightforward. Nodes with no children are called leaves. So these two fellows are called leaves because they don't have children of their own yet. Okay. So yeah. So you can see that at each level, right, the pattern will repeat itself. Okay, which means later when you do coding, you expect to do a lot of recursion here, right? So that's why we need you to be familiar with your recursion. Teachers, anything you want to chip in? Just interrupt lah. It's okay. Right. So siblings and then leaves. Okay. So and then of course because this is a binary tree, right? If you cut the tree half at the root, right, halfway point, right, you can see that actually on this side here, right, this if you remove the top one, this is actually still this node will become the root node in a sense. Okay, so this is essentially a subtree, the yellow color box. In fact, if you zoom down, come to this lower one here, right, you can also say that this single node here with these two children, right, is also a subtree on its own. Okay, so it's just the pattern will repeat itself. Okay, layer by layer. So each time you come to a node, you can check whether there's a left child, whether there's a right child or not. Okay, that's you can look downwards. You can look downwards and see what's there. All right, so left and right subtree. Okay, then these are some of the terms that you might come across. Okay, so we talk about the height of the tree. The height of the tree is from the number of edges from of the longest path. So it means how far down can I go? Okay, so in this case here, from the root node, I can go down to the next one, and next one. So I can step down by a total of, you just count how many nodes can go down by. So you say I can 1, 2, 3. If I go this side, I have 1 and 2. Okay, so the maximum number of pulp edges I can go is three edges here, right? So the height of tree is 3, 3. Yeah, have to be pronounced carefully, okay? Then the depth of the node is basically how many levels have you come down from your root node. Okay, so in this case, this is at level 0, level 1, level 2. Okay, so everything along this line here, this is level 1. Everything along this line is at level 2. Going down, this is level 3. Okay, so terms wise, there are quite a lot of new terms, so you have to be very careful, especially if it's a theory question, you need to explain yourself, right? Okay, so this binary tree. Okay, then size of tree, basically the number of nodes. Okay, so here I think this numbers here are just to count the number of nodes there are. But if this is a binary tree, this is an acceptable set of data. Okay, you choose to place them in like, okay, in this case, you think about it, right? Your order of adding in your data is basically from root create two children. Each children create from left to right, the left child, right child, left child, right child, and so on and so forth. It is a way of inserting data. But then of course, if you think about, if you choose to insert data this way, right? How are you going to access your data easily, right? So this is something you need to keep note of. Okay. So a binary tree has no, besides what the rules I told you just now about the left and right and the subtree and all, there is no other rule. You can basically choose to insert in your own way, lah. Okay, so in itself, the binary tree is just a very basic structure. Later on, when we talk about search tree, right, you can see how we can use it in a more useful way for us, right? Okay, so again, some other stuff about structure. This too, I think is good to know, not so important. Okay, a full tree, okay, which a tree in which every node except the leaves has two children. So we check. So you see, like for example, if you have a node with children, they must have two, it must have two children. Node with two children, node with two children, node with two children. So this is a full tree. Okay. Next, and then the next one, that this is a complete tree. This part is sometimes a bit harder to check. A tree in which at every level, except possibly the last, is completely filled. Okay, what does it mean? Okay, so here I have my root. Okay, then I go down next level here. Okay, so a complete tree can just be essentially a root and its two children. That is a complete tree already. Okay, because you fill up all the possible places. All right, but then now, if let's say you want to go down here, you want to go down to the next children, right? Next child, right? If you want this to be a complete tree, you make sure that both of these nodes, right, have all four children here. Okay, and then so nodes are as far left as possible, lah. Okay, this one for most of the time, I think it's good to just understand it. When you see it, then you know what is it, lah. All right. In terms of coding, we don't try to do it this way as well. At our level, we don't try to do it that way. Okay, then now, okay, so far, okay, I think we can look at the question, right? Let me just end the poll and see what we have. I don't know whether you'll see it on screen or not. Okay, can I check? Do you all see the results on screen? Oh, share results.
No, we do. Yeah, okay, we can see
Okay,
now.
so I say, okay, let's just look at question one. Question one, the root node one. Okay, let's see. Question one. Okay, what's the root node? Okay, all of you pick question option 10. So I think this is okay, lah, quite straightforward. Okay, root node is the one without any parents on. That means it's the top node. Okay, so from the root you stem out to the other nodes, right? So this is fine. Okay, then we're also asking about question 2. Which node is a child of node 3? Okay, so node 3, you can find node 3, which is over here. This is node 3. And then the child is 2 and 9. I think most of you could get it. Okay, so again, no issue. 2 and 9, no issue. You can find your child nodes. Okay. Then I think question 4, I didn't put survey because it's a similar one. Which node is the parent of node 14? Okay, so go find 14. 14 is right over here at the bottom. Then go up to find the parent. Okay, so the parent is 12. Okay, the sibling is 13. Okay, so yeah. So I don't know whether you realize this, but actually what you're looking now, right? If the numbers go inside the nodes, right, they are essentially BST already. Okay, we'll talk a little bit more about that later. Okay, question 3. Question 4. Root node has two subtrees. Which nodes are the root nodes of the two subtrees? So root node is 10. Okay, 10 has two subtrees because one side goes into 3, one side goes into 11. All right, so if you segment it out, right, number 3 here will form the left subtree, the root of the left subtree. Number 11 will form the the root of the right subtree. Okay, so from 10 branch out. Okay, so you have two subtrees, so I can just draw the line, flow my mouse down like that lah. Okay, so 3 and 11. Okay, I think we also can talk about question 5. Question 5 asking for leaf nodes. Okay, so leaf nodes by definition are nodes that do not have children. Okay, so 10 is out. Okay, 10 is the root node itself, and then 3 and 11, both of them have children. So 3 is connected to 2 and 9, so that's fine. 11 is connected to 12, so 12 is the child of 11. So basically, it's not you go from the end lah. So 2 again is not a leaf node because 2 is connected to 2 has a child at 1, and then 12 is not a leaf node because 12 has two children, 13 and 14. So in this case, your leaf nodes here are 1, 9, 13, and 14. Just quick check answer. I think some of you careless mistake. You pick number 3 and number 11. Okay, we should pick the leaf nodes. You pick the the children of the first the root. Okay, so you might be a little bit confused there. Some 4 of you pick 12 as well, which is quite interesting. Okay. Maybe if you want to clarify why you pick 12, you may want to unmute yourself and just say lah. Okay, I don't want to click results. I'm not going to click that. Can? Are we all okay with why 12 is not a leaf? Not a leaf node. Can? Okay, so as long as as long as that node has children, it is not a leaf node anymore. Okay, then let's look at 6. Okay, 6 binary tree. Okay, now this is I never put this question in because obviously I'm not going to type in all the options. Okay, so my answers are here. This is correct one. Each node can have at most 2 child nodes. It's either 0, 1, or 2. Okay, parent nodes must have 2 child nodes. No, it's 0, 1, or okay. If it's a parent, right, that means it's either 1 child or two child nodes. Okay, so it's not compulsory to have 2 nodes. Okay, nodes without children are called leaf nodes. Right, so I think that was the previous question lah. Okay, so like 1, 13, 1, 9, 13, 14 are leaf nodes. Okay, the root node is the only node without a parent. I think that one is quite straightforward. Okay, data value of the parent node must be larger than the data value of the child nodes. Okay, for binary tree, not necessarily. Okay, where I said by binary tree, you can, if you are not doing a binary search tree, right, your data can go in whichever way you want. Of course, you must have some kind of structure lah, but there's no requirement for this. Okay, next, all the data values of the nodes in the left subtree are smaller than those nodes in the right subtree. Again, because this is a binary tree, there's no requirement. Okay, then you don't have it. Okay, data values in the tree are unique. Okay, this one is similar to, I think, your hash table as well. We don't store repeated data. Okay, so basically, right, if let's say you want to, we go back to a tree here. Let's say I want to insert number 9 again, and I go in here, let's, oh, number 9 is already there, that I don't go and do a repeated insert. Okay, but of course then you may ask, like in the case of your data, right, maybe your application, you need to track multiple entries. Possible, you may want to create some kind of, you may want to create another list and link it to over here. That's fine. That one you can do on your own. But again, for us, right, at this level here, right, we only want to insert unique data values. Not going to have repeated data.
Mr. Kwong,
Ah,
allow me to interrupt
yeah.
here. Now, hash table and binary tree, they are very good kind of algorithm or technique to do searching. Then when we do searching in database, we search by the primary key, which is unique. That means you will never have a single item that appear twice. Okay, so they are all unique. So that's why when we implement our hash table and our binary tree, we normally will say that there's no repeated data. That's the reason.
Mm. Yeah. Okay. So I think we can go back to our 6, 7. Yeah. Okay. This one is binary search tree. Okay. Let's talk a bit about binary search tree. Yeah. So binary search tree is a special version of, okay, it's a special application of the binary tree lah. Tree, as long as you have each node can only have two child. I think that's the most important thing. Okay, so I think here, if you look at this slide, binary, each node stores a distinct key. Okay, all the nodes to the left of a node have keys less than the key of the node. Here, the key refers to the value inside your node, that's stored inside a node. Okay, all the keys to the right of a node have keys greater than the key of the node. Okay, so what this means is that if you look at number 6 right now, the root node number 6, right? If you draw the line down the middle of 6, right? That means all the values to the left hand side of 6, okay, from the left child onwards, right? All the values must be smaller than 6. Okay, so I have 1, 2, 3, 4, 5. They are all smaller than 6. Okay. Then on the right hand side, it must be bigger as well. So it must be bigger. So anything to the right hand side of 6 must be bigger than 6. So we have 8, 7, 9, and here, and 9 here. Okay. But you have to be careful and also look deeper into each root as well, because they say all nodes to the left. So this is not just the root node. So you come to 4 here, right? 4, that means all nodes to the left of 4 must be smaller than 4. So if 4 here, you have 2, 3, 2, 1, and 3. All 3 smaller than 4. Right of 4, I have only 5. So that's why 5 is bigger than 4. Same thing on this side, 8, then 7 on the left, 9 on the right is okay. Then the last node here, 2, has 1 on the left and 3 on the right. Okay, so make sure it's stored in the correct way, right? So these are the rules. Okay, that means now we can look at question 7. Question 7, right? All the options are the same, except for now this guy. Okay, the second last option, all the data values of the nodes in the left subtree are smaller than those nodes in the right subtree. Okay, very, very important for this. Okay, so it doesn't have to be bigger. Okay, this one actually I think is a bit of, I think it's called heap, if I remember correctly. Okay, I see anything else in the slides I need to talk about. Okay, so what can you do with a binary search tree lah? Okay, just now I think Mr. Tan mentioned hash table, right? And then yesterday we just test you on the open hashing. So open hashing, you tend to use a list. Okay, and normally if in a hash table structure, right, if there's no clash in the hash value, right, you will be able to access the data in one step. So you just hash a number, hash your input, then go straight to the correct index number you can find already. But when you have data that wants to be have the same hash value, right? They need to be sorted in the same cell in the array, right? Then you start to use a list. Okay, so right now, right, you are using a normal list. That means you have to iterate from the first one all the way to the last one. Okay, so this one here, if you look at the binary search tree, right, we can be a lot more efficient for that lah. Okay, so let's say for example, if I'm trying to find number 7, okay, if I just have a normal list that's from 1, 2, 3, 4, 5, 6, 7, 8, 9, right, if I iterate from the front, right, I need to go through 7 steps. I need to check 7 values before I hit 7 if my list is arranged in the right order. But if you look at this binary search tree, right, if you just quickly assume, let's say I'm looking for 7, right, and I encounter my root is a 6, okay, but I know 6 is not what I want, but I know that every number on the right hand side will be bigger than 6. So 7 bigger than 6, so I go to the right hand side. I come to 8 here. 8 here is not what I want also, but I know that 7 is more than 8, so I go to the left hand side. Then I come all the way down here. So once you reach the end, let's say once you reach the end, and then if you can find a number, it's good lah. Okay. Let's say I'm trying to find 0. I try to find 0. I find 0, right? I enter at 6. Okay. It's not what I want. It's smaller than 6, so I go left. 4, smaller, 0 is smaller than 4, so I go left as well. 0 is smaller than 2, go left. Once I come down to here, right, if this is not the answer I want, this is not 0, right, then I know I can stop already, because this node doesn't have any child nodes for me to go down to already. Okay, so you can see that the moment you take your first step, right, if your tree is very, very balanced, that means you have data on both sides, right, you basically is like doing by binary search, right, that you half your entire set of data already very, very quickly. Okay, so this is the advantage of you using a BST here. Can? Okay, so let's look at this question 8 now. Question 8 is a bit tricky because you have to check everything. You cannot just check one and then just stop and call a day. Like you cannot just check, oh, root node 16. Everything here is smaller than 16. Okay, then everything here is bigger than 16. Okay, and I'm sorry, no. You have to check every node to check their children are arranged correctly or not. Okay, so let's do the first one. I think first one, some of you pick it. Okay, let's see. Because I think this is the hardest one. Okay, let's try. Okay, 16. Okay, is everything on the left bigger than 16? Okay, 14, 8, 7, 2, 4, 1. Okay, all bigger than 16. So it's okay. Is 10 bigger than 16? No, right? And 9 and 3 not bigger than 16 as well, right? So these three are in the wrong place. These three are in the wrong place. Okay. So I think some of you might be able to see that a binary search tree, if you pick the wrong number to start with, you get a tree that could go down only one side. Okay, so if you try to insert a sorted list into a binary search tree, right, your tree will just go down one side. You can try like say you insert a list items integer 1 to 10, okay, in that order into a binary search tree. You can see what you get. You will just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all the way to here. Okay, second one, let's see where it's correct now. Okay, 50, 17 smaller, 76 bigger. Okay, then look at this one, 17, 9 is smaller, 23 is bigger, that's fine. 9, 14 is bigger than 9, that's fine. 14, 12 is smaller than 14, so on the left. Okay, 23, 19 is smaller than 23, so that's fine. 76, 54 is smaller, and so on and so forth. Okay, so this is okay. All right, so B is one of the answers. Okay, C we can check. Okay, let's see. Let's do the first check. 55. You notice that I'm not okay. I should also actually I should check for everything. I should just check halfway point. Okay, because right now I'm checking at each node lah. Okay, so 55, everything to the right left hand side 55 is smaller. Everything to the right hand side 55 is bigger. Everything to the left of 20 is smaller. Everything left of 45 is bigger. Okay. 63 left is 59, that's fine. 63 right is 87. 87 left is 72. And then 87 right is 91.
Mr. Kwang, you go for C, you still fall into the trap of checking each nodes. When you look
Yeah.
at 55,
Uh,
you should look at everything on the right hand side.
everything on the right
Everything
hand
on the
side.
right hand side, you got 63, 59, 87, 72, 91. Okay, all these are bigger, so good.
Mm,
So you must look at it. When you look
yeah.
at 63,
Mm,
everything on the left hand side, there's only 59. But everything on the right hand side, which is 87, 72, 91, these are all bigger than 63, so it's okay. So don't look at each node at one time. Look at the whole subtree of it, the right hand side of the whole subtree.
So zoom. Okay, so your approach is to go from the root and then just cut down, look on everything on the left hand side at one go, is it?
Yes, yes, yes.
Okay,
Ah.
can let's try. So next one, 10. Okay, again draw down 10, 10, 6, 4, 8. Everything is smaller. Okay, then we can look at 6 as well. 6, 4 is smaller than and 8 is larger than, so this is fine. Now go on the right hand side, 18, 15 is smaller than smallest on the left, 21 is bigger on the right. So D is the answer as well. Okay, so next one, E. Okay, first step, don't need to do already. 2, 7, gone already. Don't need to do already. Okay, are there any other mistakes in this one? Let's check. 7, 2, 6, 5, 11. No, okay, so this is fine. Just this 7 is gone.
No,
Okay,
no, 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 no.
okay.
This is not
That's
fine.
the repeating number.
Yeah, is it?
You
But
see,
then no,
when you
right?
look at 2,
Ah,
when you look at 2,
mm.
7 is not okay, 6 is not okay, 5 is not okay, 11 is not okay.
Oh, wrong side, wrong side, wrong side. Yeah, wrong side, wrong side.
Right?
Yeah.
Because on the
5
left
is
hand
also
side
okay.
of
Yeah,
2,
yeah. Oh, my eyes are okay. Okay, next one. Okay, letters also can. So letters we just follow the ASCII value lah. So we know F is bigger than B. Okay, so okay, half it F. Okay, so everything B, A, D, C, E is fine. Go to B. A is on the left, D is on the right. That's okay. D, C on the left, E on the right. I don't know what's the best way to sort this. As in, I'm sure I'm making repeated steps in checking. I think Mr. Tan is stunned by my
No,
inability to
you fall. I mean, I don't fall. You fall into the trap of checking each element again. Now you look at
Mm,
F.
mm,
Okay, look at F. So
mm,
everything on the left hand side of F is A, B, D, C,
mm,
E. So it's fine.
mm, mm,
You look at B. On the left hand side, there's only A, so that's easy.
mm,
But you look at the right hand side of B, you have C, D, E.
mm,
You look at three of them, C, D, E. So
mm,
C, D, E, they are all bigger than B, so it's fine.
mm,
Then you look at D. D is easy because there's only one left, one right, so it's easy to find.
mm,
Now then come to F. Then
mm.
look at the right hand
Maybe.
side. So you got G, I, H. So they're all
Okay,
okay.
so you look at F and G first, then you look at G and I, right?
No, when I look at F, I will look at three notes, the G, I, H for
G I
F.
oh, one shot look down.
I
That
look
one
at all
okay.
the three.
Okay.
Then
So
when
one
I look
shot
at
go down lah.
yes, when I
Uh,
look at G,
mm,
okay, I will look at the right hand side. So H and I,
mm.
H and I actually belongs to the right hand side of G.
Right hand side of G, correct?
Yes, H
Mm,
and I, they are actually belongs to the right hand side of G.
mm, mm,
So we need to make sure that H and I is indeed, they are indeed bigger than G.
mm,
So H
mm,
and I, they are bigger than G, so it's fine.
mm,
Then
mm.
lastly, you look at I,
I
and
H.
then H.
Yeah.
H is smaller than I, so it's on
Mm,
the left hand side, so it's okay. So I look at the whole group of it rather than
mm,
look at the
mm,
individual item.
mm, mm. I think not entirely different lah. I just yeah, because I chop half first, then I look everything here, then I chop half at B to A and D. But I think okay, if I think in terms of coding they don't have to do it, but then yeah, if you are coding in my way, you might have a lot of repeated steps lah. Yeah. Okay. So this is question 8 already. Then do I want to look at question 9? Okay, question 9 I don't have a way to draw for. Okay, can y'all? We have about 15. We have about 10 minutes left. Let's see question 9, question 10. Okay, okay. Question 9 and question 10. Right. Can you try to do on your own? Okay, let me try to open up a Google sheet to do it.
Actually, I think it's okay to let them do it on their
Yeah,
own.
try
Then
lah, try.
tomorrow, when we see them in
Oh,
lesson, we get them to share the strategy
mm,
for question 10. How did they draw that? You
mm,
know, how did they draw it? But
mm.
can I explain about the activity itself? If you look at the whole, because last year when my student do this
Oh,
question, they didn't see the black arrow, no. So what it means that you start with the number
10.
10.
Mm,
So you put the number 10 into an empty binary tree,
mm,
and then after that you try to put in the 6. So you
mm.
have to decide where
Exact.
to put 6, left or right
Uh,
hand side, that kind of thing. Then after you put that in already, then you try to put
mm,
7, either
mm,
left or right.
mm,
Then you go to 14. After 14,
mm.
please go and insert number 4.
4.
Not insert number 18, insert number 4. So you put the number 4 into the binary tree. So from 4, 12, 11, 1, 18, 3, 15, 19, the end, the last number is number 9. So you come up with your binary search tree. But so not only you must get the binary search tree done correctly,
Mm,
the next question, number 10, you have to
explain.
explain how do you do it?
Uh,
How do you do it? What's your strategy? What do you do? So then tomorrow that will be a very good interaction. We get everybody to share, and then we have all the method.
actually tomorrow don't have, because tomorrow S12 doing checkpoint and then finishing up the linear search lah. But it's okay
Yeah.
lah. I think this is, you can take over the weekend too. So reminder, algorithm don't need to give all the technical details in terms of what value you assign, what variable you assign, etc. Just tell me what is the decision that you're making when you put in your root node, then you put in the next node, right? How do you decide go left or go right? Okay, be clear. Okay, for those of you who don't know how to do this, right, go into, let's say, your Google Drive. Okay, do a new sheet. Okay, or diagram lah. Then what I like to do is that sorry, not sheet. What am I doing? Presentation. New, new. What's presentation? Oh, Google Slides. Google Slides. Okay, so just take an empty slide like this. Okay, just delete other stuff you don't need lah. Okay, I'm showing you this because I think some of you know how to code but don't know how to do this kind of basic stuff. Okay, so just put in the first number is 10, right? I think the 10. Let me check. First number, 10 and 6. Okay, so just double click inside, then you can type 10. Okay, then make it look pretty lah. Okay, you decide. Okay, so just then after you can draw lines, draw lines to go and connect them. Okay, etc. etc. So do this, then take a screenshot and then put into your answer. Okay.
Okay.
We
When Mr. Kwang say tell us,
mm,
please, in exam, you don't use verbal tell us. In exam, you have to write in complete sentences.
oh
So that the Angmo in Cambridge can
yeah.
understand your language. So you write Singlish, they don't understand, you don't get the mark. Simple as that.
Yes.
Okay.
Yeah. So yeah, pretty a bit lah. Okay. Can. So we give you the last. I think we can. I don't think we want to take out the last 5 minutes. So if you want to, you can take the time and do this, or they can go off. Okay.
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 Mr. Kwang,
Yeah.
just now when you draw the sheet, can you draw one more circle? You
Oh.
draw one more circle or copy the circle.
Okay.
I just now just caught my eye that yeah, just copy one more and let's say this is number 6.
Oh.
Okay, so never mind, we give them the answer. Okay, 6.
Oh.
Okay, are you going to put on left hand side or right hand side? Connect that with the line.
So 6
Okay,
lah.
you connect the line. You see the line can join the dots,
Yeah. Yeah.
Okay, you drag the dots. You connect the dot. Now you shift the
Yeah.
circle.
Yeah.
You see, the line will follow. So if you so similar to your flow chart or this kind of thing, if you connect them to the correct joint, as you shift the whole diagram when necessary later on, the whole chunk of it will move.
I think it's
So
a
that makes it easier.
purple line here. Yeah.
Yeah,
Purple
the purple
line to
dot.
purple line.
Yeah.
If you put you put anywhere else, it doesn't work lah. Let's say put
Yeah.
here, it doesn't work. Okay. So you have to connect it. Okay.
You
So
connect it. Then that's very convenient. Right, you move the whole thing. Okay, I think that's all I have.
Can. Okay. If you don't have any questions, you can unmute, say bye bye, and go off already. Okay.
Bye bye.
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 Bye bye.
Bye.
Bye bye.
Bye.
Thank
Bye
you.
and
Bye
have a nice
bye.
day.
You too. Have a nice day.
So
Yeah.
for like question 9, right? Like you only need to
Nine.
ensure that the left side is like the value is smaller than the right side can already or
So if let's say, so you insert, okay, you insert this 10, 6, 7, 14, 4, 12, 18 until 3, until 9, correct? So whatever you put in, you always start from the top lah. Okay, so you want to put in, let's say number 7, right? 7 is smaller than 10, right?
yeah.
So go where?
Go
Left
at
or
the
right?
left side.
Left hand side. So you can't come to 6. So go 6, then is 7 bigger or smaller?
Bigger.
So go where? Left or right?
Right.
Keep on going like that lor.
Oh, okay.
Okay, can?
Okay, thanks.
Alright.
Thank you, John. Bye.
Who else is left?
Okay.
Okay. Joshua is okay lah. Never mind, you can hear. So Miss Chua was telling Mr. Tan for next week because there's physics practical, so I'm involved lah. So two of you need to take the online lesson. So I think going by the number of lessons we have before next Thursday, we should be towards the end of binary search tree, the traversal part lah. So that one can be done online.
Okay.
Then we can prepare to start sorting from end of next week onwards. That means week 9 onwards.
Yeah.
So
Miss Chiu, you get ready your bubble sort lah.
Yeah, I
Correct.
prepared. I bought the cards. I brought them to school already. So next week I'll ask each class to give me a rep to go and distribute the cards.
How many did you buy?
I have 7 packs of 50 cards each. Actually
7?
not enough because they say cards from 1 to 100, right? But what they didn't tell me was the cards are printed on both sides. So each pack only got 50 cards. So each student will get about 7 to 8 cards, which I feel for.
Which I feel for 7 or 50, right? 7 or 50 cards, right?
Yeah, 50
yeah.
So
give them about 6 or 7 lor.
Yeah. Should be enough for the basic sort, but once they once they come to merge, actually they might need more I feel.
Correct.
But they can combine and do which is also okay.
Correct lah. So you get them to combine the 2 sets together, and the small kind of easy one, you can do it on the alone and that kind of thing. Then when they want a bigger set of number, you can combine.
I will ask the class rep to try their best to have in every set to have 2 cards with same number.
Don't deal with same number.
Because
those are
I think
trivial
it's,
case because when it comes to same number, it depends on the requirement
stable
of the
and
question.
unstable, right? Yeah.
Yeah, so that one we don't get ourselves involved in that.
Okay, lor, can.
Yeah.
Then just
Also, the
randomize
main
lah.
thing is that when we give out the student the card, they must I tell them that they must keep it because we got to pull through all the sorting algorithm.
Yeah.
Don't lose it.
Yeah. Okay,
Yeah.
can. I think
Can.
that's all.
Okay.
Thank
Have a
you.
good day. Bye.
Bye, guys.
Bye.
Bye.